Thanks for the intro, JML. I hope we all had a good lunch. I did. So it's my second year at the Canadian Tech at Scale, and I had a very fantastic time last year. First one was I got to meet all great people like yourself and build a network and learn about all other things that are happening in Canada. And the second reason is a bit personal. See, I got to take a break from my life in Ottawa and come to Toronto when my house looked like this. So it's a bit of a mess. And I want to point out the coffee machine that, despite all of the craziness, is still working on the corner. So my partner and I had started to renovate our kitchen, and we had a very clear idea of what we wanted the output to look like. But as a computer scientist and a data scientist, we really didn't know the set of sort of pragmatic steps that we had to take to get from here to where we wanted to go. So we started looking out there, and there's a lot on the internet. There's a lot of good material, and there's a lot of noise. There are people that are trying to sell you the shiniest tool available, and it's going to be great for cutting your countertops, but it's also great if you want to switch your whole career and do nothing but cutting countertops. So it's a little bit much for what we wanted to do. So as we started looking around, we learned how to filter information and get to the essential, to the things that we needed to do to get to the end. Now, you might be thinking, like, wow, is this a construction conference? I suggested that to JML, and he said maybe next year. So stay tuned. Now, this is a talk about how to make data products scale. And when I look outside and when I start looking for material out there that would walk someone from where they stand today, where they have a product, where they want to bring a little bit of smartness, and they go out and they look around, what I find is very similar to what I found when I was trying to renovate my kitchen. There's a lot out there, and there's a lot of noise out there. So at Shopify, we took this path 3 years ago. We started bringing simple machine learning to our products, and we've gone through that and been able to bring this to 3 different products, generate revenue, and we do it with a very lean and scalable way. So I thought maybe I can walk all of you through this, and what would make me really happy and what's my goal from this talk is for every single person to be able to walk out of here with 10 easy steps that they can follow that's buzzword-free, technology-independent, and would scale with their business. So let me give you a little bit of context about Shopify. I'm sure everyone knows it. We are a commerce platform. We are a leading commerce platform. We are cloud-based. We allow people to sell everywhere. And our mission, like very core to our business, is that our mandate is to make commerce better for everyone. Now, while this is Shopify's mandate, my team's mandate over the last 3 years has been to make Shopify smarter for everyone, but with 2 conditions. First one is that we still want to keep the platform resilient. The resiliency of our platform is something that is one of the high values we have. So we didn't want to say, you know what, we're going to bring machine learning to the product, but every 2 hours, maybe we would have a 5-minute downtime. But machine learning is cool enough, so we're going to do that. No, we wanted to keep our resiliency standard as high as it has always been. The other aspect is scalability. So we wanted whatever we build to work for every merchant. So merchants that are small and they only have 1 or 2 orders a day, and merchants that are massive or enterprise level, and they might have thousands of orders per minute. So whatever we brought with my team had to satisfy these 2 conditions. So we got started. So what's the first problem? The first problem is actually what's the actual problem we are going to solve. It's really important to find something to make smart that users actually care about, something that they're going to go and use day in, day out, so you can get some feedback, some data, and learn, is your solution actually working or not? The other aspect of it was that we wanted to pick something that we had a lot of data on, because nothing is going to beat good data for machine learning. Like, if you have good data that can tell you about the problem, you're more than half of the way there. So when we started looking, we found one of the first problems that we can tackle is our order fraud detection. So for every order that comes through Shopify platform, we want to be able to classify that order and say, is it fraudulent or is it not fraudulent? And having sales is something that's common across the platform. So it's going to be a problem for every merchant. And we have lots of data because we've been processing these transactions for the past 10 years. And the other condition that we had in mind is not really about data, but it's about the UX and product aspect of the problem. So we wanted to pick something that's not the core competency of our merchants. It's not something that's the sole purpose of them coming to the platform. Our users are entrepreneurs. Their main goal is to create the best product, put it in front of the right audience, and have a sale. By becoming better risk analysts, they actually don't become better entrepreneurs. So they would want us to take something so burdensome off of their shoulders and build something for them. So that's how we got started. Well, you might not pick the same problem, but the same conditions are going to be able to guide you to the problem that you want to solve. So let's learn a little bit about the flow of the order fraud detection, because I'm going to make our examples around those. So a buyer goes to a Shopify store, and they place an order. And a merchant is super happy. They have received an order. They look at the order, and they don't see anything suspicious. They look for a few things that they've maybe heard on forums, or they think, oh, if this buyer is from this country, maybe there's more higher chance of fraud. But they don't see any of those. So they're happy, they fulfill it, and they ship the item. 1 to 6 months goes by, and the merchant receives a note from the bank saying that, oh, actually, that order was placed with a stolen credit card. In these scenarios, the banks and credit card companies always side with the buyer. They say, well, they didn't know that the card was stolen, so they take the money away from the merchant. And the merchant has already sent the goods as well, so they're out of the goods that they are selling. And on top of that, they have to pay a chargeback fee. So it's like triple negative for them. And also, it's an emotional strain. From the data side, it's also a very good prediction problem. It's a simple classification where you have a bunch of data and you want to decide if the next example is going to be fraud or not fraud. So we picked that as our first problem. But we started to understand the flow of events, because whatever you try to solve, it's not going to be an abstract, isolated problem. There's going to be downstream things that depend on it. So in Shopify, we realized that we needed to detect fraud before the order was fulfilled. Because by the time the order is sent out, the merchant's out of the goods anyway, so our prediction is not that useful. That simple condition actually translates to engineering constraints. So it means that our system has to be able to do real-time evaluation. So the moment order comes in, we have to be able to, at the moment that the order is placed, be able to evaluate the risk of it fraudness. The second thing about our platform is that our checkout is our heartbeat. We don't want anything to slow it down. So if I had gone back and told our production engineering that I have this amazing model, but it's going to take 5 minutes, and it's going to slow down every checkout 5 minutes before it gives you the result, they would have called bullshit, and none of this would have happened. And then it had to scale for all merchants. So some of the merchants are going to have lots of sales. We're going to see lots of data from them. But then there's also going to be merchants that just are starting on the platform, and we haven't seen lots of history from them. So we had to solve the problem for that as well. In peak time also, Shopify platform sees around 6,000 orders per minute. So that means an order every 10 milliseconds. So these are serious conditions that we had to meet. And also the accuracy of prediction. If you want the users to listen to your prediction or recommendation, you also have to think about the implications these are going to have in their life. So if we tell a merchant to cancel an order, then they listen to us and they cancel it, and it's a legitimate sale. We've cut them out. They realize it's a tourist shop, and they sold tickets to an attraction in New York City. So the people who bought the tickets are visitors to New York City, and they're going to pick it up in New York City. So the shipping address is in New York. The billing address is somewhere, wherever they live. So this mismatch continuously was raising the fraud flag. Now, a human, the store owner, would look at this and after the first time probably say, oh, that doesn't make sense, and continue to fulfill. But our system was not learning from this rich history that we were collecting all the time. As a result, with this rule and other rules, we had a very high false positive. So there was lots of orders that we were marking them as a fraud or for the merchants to investigate. So investigating an order means they have to call the buyer, they have to spend a few minutes. It's not something that they're really built for. They don't have the skill set, and it's also a waste of their time. So all of this, we thought, okay, that's a good problem for us to start to tackle. So the second point is that, do we actually have data around this? So I love this, because I talk to people in other companies, and they tell me a problem they're solving, and I say, do you have data? And they're like, oh, yeah, we've been collecting data for the last 10 years. Everything is there. It's awesome. And then I say, okay, is there data that someone can access that's trustworthy and can be used? Or do they have to call an ops person to move data from an S3 bucket to somewhere? So they're like, oh, yeah, OK. So no, not that data, but the data that can be used day to day, that can be loaded into a medium that your data scientist can use. So at Shopify, we also have this fundamental belief that data is one of our biggest assets. So we have been collecting data, and for the most part, we can access our data. A wide range of our data we can easily access, and the other ones we have ways to get at them. I'm going to tell you what our infrastructure is, but whatever you have for your data warehouse is going to work as well. As I said, it's not really technology dependent. We get all of our data from source systems to HDFS. Our data warehouse is an in-house built platform by our amazing data infrastructure team. It's built on top of PySpark. Everything runs on a scheduler with Uzi. Then we write data back to HDFS, and our data scientists can access it a few ways. We load it into Presto, we load it into, well, it's in Hadoop, and you can load it into various tools, and we can also push data back into Kafka, which means there is an out to other systems that can use this data. So step 3 is that whatever problem you pick, as Inmar said beautifully last year, is a mathematical function that you're trying to solve. Machine learning in its core is a method. It has a bunch of inputs, and and it's a desired output. So in the machine learning lingo, we call the inputs the features, and the output is the target, whatever you want to predict or you want to find what's familiar with or what's it's similar to. But it's one of the most important steps. In fact, to me, feature selection and feature engineering, perhaps once you iron out all the technical details, is the part that still needs a lot of art and a lot of good data science work. And the first step is, if you don't know what are the features for what you're trying to solve, is go and talk to people that have the domain expertise. So one of the things we did is that we actually have risk analysts that work on detecting fraud on Shopify. And they look at different profiles every day. So we went and talked to them and said, OK, well, if you were to look at this order, what are the things that would trigger you to do more investigation? And I think that's one of the key points that when you get started on a problem, you shouldn't miss. It's not humans versus machines. It's actually a collaboration. And whatever you can learn from somebody else, like, don't waste your time digging in the data to find that again. So once we understood a little bit more about the problem, we realized, OK, we have to actually define what our target variable is. Now, when I started it, it sounded very simple, right? We want to predict what orders are fraud. And I said to you that we have lots of data. Well, we do, but when you start looking at it, there's so many gotchas in there. The first one is that it takes us 1 to 6 months to receive chargeback status of an order. So in reality, for a machine learning model, it means that if we were to wait the 6 months, we actually have to wait 6 months before we can ship a new model, before we can assess the goodness of our model. With the speed of things at Shopify, that is not very desirable. So we started looking at the distribution of the times that we get the chargeback. And we were able to push that a little bit back and less than 6 months and be able to train and test our models in a much faster framework. The other point is that, so we had a table, it had the disputes in it. And that means that the order had the dispute. Not so much. When you start looking at it, you realize that we had defined our problem very clearly as finding the fraudulent chargebacks. But disputes can be of many types. So not every dispute in that table was what would be a target variable for us. So by starting to look at the data and actually, like, if you have documentation around data, that's good. Sometimes we don't. Dig in the code, dig into the API documents if you're getting data from somewhere else. And we understood that, no, there's this other condition that has to be true. So it has to be a fraudulent dispute for us to put it as target. And then everyone who gets data from third parties, you're a little bit at the mercy of their definition. So if we are getting the definition of chargeback from a bank, we basically rely on what a bank is calling a chargeback. Maybe in your case, it's not chargebacks. Maybe it's like another thing that you're receiving from a third party. But more often than not, they don't ping you automatically to say the definition has changed. So I think this is one of those things to have a check mark, to revisit time after time to make sure it hasn't changed under your feet. Because as soon as your target has moved, what you are predicting is not what you thought you were predicting. The same sort of discussion goes for the features. So again, in the beginning, I said I had tens of years of orders, and there's so much features in there. So we started building some simple models. The first thing we noticed is that we had this feature. It was amazing. Every time that that feature had the value 1, the order was fraudulent. I mean, it's like a little bit too good to be true. So we started digging and realized, oh, this is a signal that the credit card company sends a few weeks after a credit card has been stolen and has been used across the network. So they've already seen fraud on it, and they ping us back and say, hey, heads up, there might be fraud. So in a sense, we were not predicting fraud. We were seeing fraud in future. For us, it's not possible as humans to have leaking information from future into past. In data, that's really easy. So whatever feature you pick, make sure that the system that's going to evaluate your instances is going to have that feature at the time of evaluation. So for us, we had to scrap that feature. The other part is it's amazing to be in a startup. You ask for a data point, and you can quickly start to collect it, and people are super collaborative at Shopify. But the other side holds as well. Because we're a startup and because we move very quickly, we also change our underlying data models quite often. So again, we had this feature. It had a decent predictive value. But when we started looking, we said, oh, this actually hasn't been fired for the last 6 months. So something somewhere has changed, and we were not getting that data anymore. And then keeping an eye on the changes in the behavior of the feature. So 3-4 years ago, placing orders on a mobile device was not very common. Because it was not very common, the rate of fraud on it was also very low, right? Not many people, it's a game of numbers. But 2 years ago, we passed this landmark where we have more orders coming from a mobile device than a desktop. So if previously we had said an order being from mobile means it's not going to be fraudulent, then that feature was not holding true anymore. So we figured out some of these checks, the recency, the frequency checks. But what made us be able to scale was that we said, okay, our data scientists are way more valuable than having to remember to do every single one of these every time they are doing feature engineering. So we actually built templates that can automatically run on our features and give us the statistics. And only when a feature has passed those, we start looking at it in more detail and adding it to models. Step 4 is that there are many algorithms out there. And the state of research is pushing new ones every day. The science is moving so fast in this domain, and in Canada especially, we are so lucky to get so many new papers published every day. Those are great, but you do not need those to get started. Most of us can start from very simple algorithms to bring some value to the product before we go to the latest research. And just to see how simple it is, one of my favorite things is this page on scikit-learn, which is Python's main machine learning library. So if you go there and you say, okay, if you know as much as if you're doing a classification or a regression or clustering, literally it has a workflow, it has a flowchart that walks you through what kind of algorithms you can start with. And for us, we started from the simplest thing for classification. We started from a logistic regression. And guess what? We were still able to get an 80% lift, because the first time you go from a rule-based system to machine learning is the time that you're going to get the most gain for the product anyway. And once you figure out your whole workflow, there's no stopping to go back and visit better algorithms. But to start, I would always advise to start with the simplest thing so that everyone can understand what's going on. So step 5 for myself, coming from a research background, was the one that got me. So all of this work that we are doing in Shopify, all of the work that you guys are going to go back and do in your companies, is not an exercise in data science. It has to be solved from a product perspective. So what do I mean by that? When I was in academia, I would solve a problem, and I would have very good predictive value for a feature, or I would have a model with very good accuracy or very good precision and recall. And those were the things that made me think I have a very good model. But when you move to products are going to be used by real humans, and humans have different expectations. So just the fact that the model is the best one in accuracy doesn't mean it's going to result in the best user experience. To give you an example of how it works in fraud, is that you can think of the extreme case that if I call every order as fraudulent, the merchant would never fulfill anything, and they would never have any fraud. And my model would be very good from that perspective if I was optimizing for less false positives. But here, for example, at Shopify, we want to help merchants sell more. So we put an emphasis on maximizing their sales. So knowing that actually has implications on how we optimize our models, where we put our thresholds. The second thing is that most of the time, industries have benchmarks. There are things that people and users are used to seeing. So for example, in risk industry, there are known percentage of orders that are supposed to be called fraudulent, known percentage of orders that the merchants need to investigate. So while you can go and shift all of the industry, but if you're going in an existing product, you have to make sure the users land on a soft land, they have a soft landing so that they can continue to use your product. For us, it was very important to make sure our models are not exactly, but close enough to those industry benchmarks. And then think about the humans that are going to use these models, because every prediction that we make goes in front of a user who's a human who has a busy day, and this is the last thing they want to do. So if we tell them that this order is fraudulent and it's not, what's the implication for them going to be? And if we make another wrong prediction, is it going to make them close their store or not? And having a concept of like, what's the actual cost of mistake to the user is one of the other things that we check in our models. I cannot emphasize this one enough. So we invested a lot in our good data engineering practices. We wanted to get something quick and dirty out the door, but like the more we went through that feature engineering cycle, that model building cycle, the more we realized that the data scientists are spending their time in toil, something that would make them just distracted and not interested. So we made pipelines that are really easy to understand for the people that work with them. We call out what our input data is, what our data types are. We call out the transformations on the inputs very clearly, so that if we take this model and move it to another system, those transformations are not lost. An example is that, for example, if when we are training the models, we have a binary variable, and it can be yes and it can be no. But sometimes there's missing data and it's null. So if in data land, I translate null to no, and then randomly this goes to another system and they translate null to yes, well, the model is not wrong, but the data it's getting is wrong. So calling out these transformations and having, or whatever you do, but having tested pipelines takes so much work out of the day-to-day of your team. We've done lots of work here. So we have a very rich layer of metadata in our engineering. So for example, we know for every model what were the exact inputs that went into it for training, what's the exact data set that was used for testing. And then we do this last step, which is very common in financial institutes, and that's where I learned in my previous life when I worked at Morgan Stanley, is called backtesting. So if you're a financier and you have a new strategy and you want to bring it to market, you actually might not know how it's going to do in the markets yet. So you run it in the most recent set of data you have, and you compare it to the other strategies. So we do that with our models. So when we have a new model, and as I said, it can take us up to 6 months to get the true results. So we run the model on the last 6 months of the data, and we just look at the results of the prediction. So if the existing model was putting, for example, 90% of the orders of a merchant in accept, and the old model was putting 90% in accept, and now we are putting 98% in accept, the experience of that single user is going to change drastically. So running these checks allows us to reach out to those merchants and explain to them. First of all, we have to figure out is there a bug in our system. Sometimes we've found bugs that way. But if not, reach out to the merchant beforehand and make sure they understand what's going to happen to them. Step 7 is how are these models deployed? So all that I was talking about so far was building these models. In Shopify, we have this tale of two platforms. Our data land is everything is in Python and Spark, and our application is a Ruby on Rails application. The whole point of fraud detection, as I said in the beginning, was to run at the time that the order is placed. So if I cannot have this model where it needs to be evaluated, all I've done is useless. Now, some people say, well, why didn't you build a new application in Python and stand that up? Well, because Shopify is really good in Ruby on Rails. And our production engineering team has made keeping these applications up and running 24/7 really easy. So while we could have gone out and built a new application, the pros of going with the existing system was much higher for us. So the first time we did it is the hackiest thing you can imagine. We had a logistic regression. We took the coefficients, and we hard-coded them in Ruby. And it still bothers me, but we did a lot of checks. Like, you can imagine that PR had so many sets of eyes on it, and I still am like, what if we missed something? Luckily, we fixed it very quickly. So we hard-coded the logistic regression there, and it was at the last point that basically we had to show the results to the merchant. And the point of it was to show the company that, yes, we can do this. If we had taken 2 years to build the perfect pipeline on the first try, sure, we wouldn't have this experience. But maybe they had given up and they have gone out and did something else while we were figuring it out. So in the beginning, we went with something that wasn't great. But we also knew that that's one of the things we have to fix right away. So one of the leads on my team, Kyle, who is sitting there, You can talk to him about this because this is going to be super useful for lots of people. While we were trying to figure out how we take a model that we've trained in Python and bring it somehow to Ruby, we realized, Kyle went and found PMML, which is an existing standard. It's Predictive Model Markup Language. It's XML of predictive model. It's been around a lot, and it's mostly used in academic settings. But what he found was that Python and Spark, both of them natively have functionality to move models to PMML. So in simple word, it means like if I train a model in Python, I can save it as this XML document that not only has all of the inputs, but also has all of those transformations and all of the things that we want them to be the same between the two systems. And then he started working on a Ruby evaluator for PMML. So right now, we save our models as PMML. We have this XML document. Then we have an evaluator in Ruby where we load this XML document in it, so it doesn't need to know Python or anything else, and it can evaluate these basically data as it comes real time in our Ruby on Rails application. And we're going to open source that gem, which is called POML soon, so stay tuned for that. The best thing about this is that we did not have to go and hire another team which wrote all of Python's machine learning in Ruby, and maybe one or two people that continuously check these two against each other. So by looking around a little bit, we were able to find something that solves our problem. And then I always get this question, but PMML is not going to work for this or that. Yes, but it worked for us. So the solution you find doesn't need to work for everything. It doesn't. I really like the note that was mentioned this morning. You do not need to build your system for 100x of what you want. If you can build it for 10x of what you want, it gets you going, and then you can revisit and refactor. So going through all of this, now we were able to have a model that's trained in Python. We have done all the tests and serialized to PMML, and now it's loaded in a Ruby application. So it's almost ready to meet the merchants, but not yet. So after the first model, you're always introducing new models to your merchant base or to your user base, right? They're used to some behavior, they're used to some SLA, and you're going to change it. So we run a lot of checks before introducing any new models with consequences to our merchants. What we call live model backtest is this practice where we put the model in the production environment, and it runs in shadow. So what it means that our risk engineering team has built this functionality in the app that allows us to send every order that comes in to the model, but the output doesn't go to the user. The output goes on a Kafka queue, and what we do at the end is that we compare the inputs that the model saw in production with the inputs that the model saw in data land, because we are building on top assumption that these two are going to be the same. And once the inputs are the same, we also check the outputs, and once all of those checks are good, we deploy the model to basically we power the user experience with it. This also helps us learn about intricacies in our system. For example, sometimes we realize that the data asset server that we reach out to might have a different version of data than what the data LAN had. And it has always basically opened our eyes to something that would have been missed. So after all of this, we have a model, it can go live. Cool. If my team had to do all of this every single day, we would still be at the first product we did and probably not far ahead. But we took the time to automate all of these things. So all of the things I told you run every day on a schedule for all of the merchants and all of their orders. That has allowed us to do much more than just I went through. We have been able to look more into our model operations, because models, once you put them in production, they are living, breathing things. They have a life of their own, and they have implications on life of other people. So one of the things that we have started to do is to detect changes in the feature distribution. So for example, if till yesterday we were seeing lots of orders coming from Germany, and all of a sudden that goes down, there's nothing that would alert us, right? Because this model is in production, it's producing some results. So we have made it automatic checks that control for these things. And so in the beginning, of course, we had these checks, and somebody in the morning would run the report, would look at it. But then we realized that's really not a good use of our time. So we have automated that, and it now pops into Slack channel, and the ATC at the day can take a look and investigate if something is important. This whole pipeline has allowed us to deploy models very fast. So we are now able to retrain our models, the same model, and deploy a new trained version every 2 weeks. We can bring new models with new features once a month if we are ready for that. Usually there are other aspects that slowed us, not the deployment and not this pipeline. Basically, we've taken most of the toil out of the day-to-day of data scientists and have given them tools that they can add value where they are best at. Some of the things we want to figure out is model versioning. So if any of you have tackled that, I would love to talk to you. And we have some opinions, but we haven't really done that in production much yet. The future we want to go to is automatic model deployment. So we actually want our data pipeline to post to the app the new model and make it deployed. And it's not for the lack of technology. Like, we know technologically how to do it, but we want to understand, like, what are the implications, what are the good checks to have in place before we go there. So step 10, wash, rinse, repeat. Having this pipeline has allowed us to not only do this for our fraud detection, but has allowed us to ship 3 other products in this time span that use machine learning. Our Shopify Capital, where we give cash to our merchants to help them grow their business, which means we have to be able to predict their future sales with very good accuracy, benefits from the same pipeline. We just announced our Fraud Protect product, which sits on top of our order fraud detection. And in shipping, we're taking the same steps to bring some of the smartness to our merchants. Step 0 is the most important one, and it's the one that you have to start with, because without that, none of this would be possible, is to build the right team. More often, people think of it as either an engineering exercise or a data exercise. In reality, this is a full stack problem, and we were able to succeed because we have a full stack team. So I lead our risk engineering and risk algorithms team. So it means like we have full alignment between the 2 sides. There is one roadmap, and that has helped us immensely. For the first thing that comes to my mind is that there's so much understanding and empathy between the 2 sides of the organization that we don't have those sort of classic challenges of, oh, I want data, but it's not available, or, oh, these data scientists don't know how to scale things. People sit together. People have an understanding of day in, day out of each other's life. And for example, if the algorithm teams ask for a new feature, the engineering team feels comfortable to say, so what's the lift, how much better this model is, and is it worth the strain that's going to put on the engineering side? Having all of that has allowed us to have very lean teams. So all of the things I talked about were built by 4 data scientists. Interestingly, people always ask me, so how many people with PhDs do you have? We have 1 person with PhD, and she's an amazing data engineer and data scientist. But the person who pairs with her all the time and they work together as a duo is someone who joined Shopify right after high school. So don't get blocked on the titles or education of people if you want to hire people for building these teams. At the end, the most important one is the team you build. So I hope you go out and make your products smarter for all of your users. And about my kitchen, if anyone had questions.